topic of imaginary numbers. First, I'm going to conduct some one-on-one interviews to see what you already know about this topic. Now, doesn't that sound like fun? Now, I will admit that imaginary numbers can be a hard topic to understand. However, you probably already know more than you think. All it takes is some imagination and thinking outside of the box. Meredith, you're up first.
Fine.
Now, Meredith, what do you know about imaginary numbers? It's okay if you aren't familiar with them, but I want you to get a general idea of what you may already know.
Imaginary numbers? That sounds boring and hard. I'd rather be shopping.
Well, let's give it a try. It may be more interesting than you think. Let's start with a simpler problem to understand. Solve the equation 2x minus 6 equals 0.
I added 6 to both sides and then divided by 2 to get x equals 3.
Well, that's easy, but how does that have anything to do with imaginary numbers?
Well, now that you know you have a general understanding of how to switch back and forth between operations in order to solve a problem, all you have to do is apply that to more difficult problems. Like imaginary numbers. Here's a more complex one. In this problem, we are dealing with cubed root in imaginary numbers. All you have to do is prove that both sides equal each other. To do that, we are going to cube 2 plus I. Then we are going to use FOIL to solve the equation. This is the same concept we used in the previous problem, with simple mathematical operations.
Oh, that's easy. I already knew how to do that.
That's great, Meredith, but let's stick around and bring Jess in so we can talk about some more.
Not to be rude, but I already know how to do the problems Meredith just did. I don't need to know anymore.
You may want to rethink that. Let's take a look at some graphs. What kind of graph this is?
Yes, Cartesian.
What about this graph?
I've never seen that kind of graph before.
It's called an Argand graph. It looks very similar to the Cartesian plane. But notice how on the y-axis there aren't real numbers like 1, 2, 3. There are complex numbers like I, 2i, 3i, and the x-axis is the same. See, isn't this pretty easy? Just remember that when graphing on the Argand plane, draw a line from the point to the origin if you want to find out more information about it.
Wow, this is better than a sale at Macy's.
This isn't the only thing we can learn using graphs.
No way! What else?
We can use graphs to learn about degrees and radians. First, let's talk about degrees. Let's say that you are graphing the point 5, -5 on the Cartesian plane. Once you plot this point, you have to find the degree measure for the line it lies on. First, you start at 0 degrees and work your way counterclockwise until you reach the point. Then you can take a protractor and find the angle, and then subtract that from the entire 360 degrees to get a final answer of 315 degrees. Radians are just as simple. Say you have a point on the y-axis. We describe its angle in terms of pi instead of degrees. In these terms, 180 degrees is equal to pi. So if the point is on the y-axis, you would say its angle measure is pi over 2 radians. Let's talk about numbers in their relation to the physical world.
But you can't hold numbers.
Well, Jess, you would be surprised. Numbers are used when you buy something and you need to get change back. And another example would be when you're baking. It's important to add the right number of eggs or the right amount of flour. So while it may not be easy to see complex numbers in the real world, we know that real numbers do exist and that we can see them.